All right, good morning, everyone. My name is Charles Harris. Today I'm going to summarize Chib and Greenberg's 1995 paper, Understanding the Metropolis-Hastings Algorithm. So, Metropolis-Hastings is an example of a Markov chain Monte Carlo simulation. These MCMC methods have become increasingly popular for simulating complex, non-standard, multivariate distributions. Perhaps the best known of these is the Gibbs sampler. And while there had been a fair amount of literature on that algorithm at the time of this paper's publication, Chib and Greenberg felt that there was not an adequate summarization of the MH algorithm. So in some ways, this paper is a response to and a companion of Casella and George's 1992 paper explaining the Gibbs sampler. And I believe our classmate Jung Xiaojin plans to present that one. Of note, while the Metropolis-Hastings algorithm has been heavily used in physics, it's only more recently been adopted by statisticians and economists. So first, we're going to start with a little bit of history and background in this. The Metropolis-Hastings algorithm was developed by Nicholas Metropolis, Edward Teller, his wife Augusta Teller, and then Marshall Rosenbluth and his wife Ariana Rosenbluth. All of these individuals were working at the U.S. Nuclear Research Lab in Los Alamos, New Mexico. And so they were studying specifically state transfer. And so if you look down here, this is kind of a typical phase diagram where we'll show a material transitioning between solid, liquid, and gas at different temperatures and pressures. And so they were trying to model these somewhat complicated phase change diagrams for different materials. And so they had access to the Maniac 1 computer, which Nick Metropolis had been instrumental in designing and constructing. And so they used this early computer to simulate these phase change diagrams. And so in 1953, they cumulatively published a paper, Equation of State Calculations by Fast Computing Machines, in the Journal of Chemical Physics. Of note, though, while Nick Metropolis's name went on the paper, his predominant contribution was just to give access to the computer to the rest of the group. Ed Teller made an initial suggestion on how to design the algorithm that was instrumental in giving the team like the right lead and how to proceed. His wife Augusta wrote the initial version of the code, but the final code was written in its entirety by Ariana, and then most of the paper was written by Marshall Rosenbluth. And so history is given fairly little credit to Edward and Marshall, and almost none to their wives, despite them doing most of the work. And then the only one of them whose name is remembered in the name of the algorithm is Nick Metropolis, who of the people involved had the smallest contribution. Anyway, so they were using their model that they were trying to use was a hard disks in a box model. And so that's depicted here. And so the idea in their initial model was that the molecules were these little hard disks and they couldn't overlap with each other. And so they would have to find space in the material to move into. And so they needed an algorithm that would model that, trying to move to different places and seeing if that was feasible. And so that was the beginnings of the Metropolis algorithm. And then so years later, in 1970, a gentleman named Wilfred Hastings updated the algorithm, and so he published that in the paper Monte Carlo Sampling Method Using Markov Chains in Their Applications in Biometrica in 1970. And his key contribution was in allowing a non-symmetric proposal distribution, which we'll talk about later. Okay, so first we're going to talk a bit about acceptance rejection sampling. So acceptance sampling is different from Markov chain Monte Carlo methods. So it's a simulation technique that generates non-Markov samples. So the successive observations that it generates are usually statistically independent unless we've artificially introduced that. And then so of those, the AR method is an important example. And so the objective here is to generate samples from a target density pi. And so we let we let h of x be a density that we can simulate using some known method. And then we suppose a constant c such that the product of c and h of x bounds our function f of x for all x. And so if our candidate that we generate for a uniform distribution is less than the f of z divided by c times h of z, and then z becomes our new value. Otherwise, we discard it and we generate a new candidate. This is different from the MH algorithm, where if it's rejected, then the previous value becomes the new value. Of note, for this method to be efficient, we have to select C carefully, and we can show that it's optimally set between the supremum of f of x over h of x prime. But even if we do this, we still might have a large number of rejections. All right, so with Markov chain theory shows basically the relationship between different states and then a probability of move between the different states. So one example might be sunny days and rainy days, where there's some probability of a rainy day following a sunny day following a sunny day, and so on. And so we start with a transition kernel, which we define as P of XA. And so just to quickly talk about notations, I'm using the same notation that Chib and Greenberg use in their paper. Often you would see this as P of X given A, the probability of moving to X that's given that you're at A, right? So for X in the real space, then A and B is a Borel sigma field in the real domain. This represents the probability of moving from X to a point in the set of A, such that it is a distribution of X in real space equals 1. So there's a with certainty you're moving somewhere within that space, but the probability of staying at X is not necessarily 0. So there's a possibility of, like I said, sunny days remaining sunny days. And then one key consideration is that under what conditions does this generate an invariant distribution? And so we can show that when this is satisfied, pi is a Lebesgue measure of pi star, and then the nth iterate of the sequence converges to the invariant distribution. Okay, so Markov chain Monte Carlo reverses this. So we say that we know the invariant density, perhaps up to some constant multiple, right? And so this invariant distribution is the target density that we want to take samples from. But what we don't know is the transition kernel, and so that's what we're seeking to find. All right, so we want to generate samples from our target distribution. And so MC finds and uses a kernel which is P of X dy, and whose nth iterate converges to the target distribution for a large number of iterations. And And so we can start with an arbitrary x value, and then by iterating a large number of times, it eventually takes on the target distribution. Okay, so the problem then becomes finding that appropriate kernel. Okay, so if we suppose a transition kernel P with a probability of staying at x is 0, and then our delta x is 1 for x and dy, and 0 otherwise. And then we say we have r of x is the inverse of this probability. Is the probability that the chain remains at x. Since r of x is not necessarily 0, the integral of p of xy over y is not necessarily 1. And so then if pxy satisfies reversibility, then pi is the invariant density of P. So this was proposed by Tierney in 1994. And so the following is the sufficient condition that must be satisfied by P. That's that pi of x, px of y equals pi of y, py, and x. And so the left hand of the reversibility condition is the unconditional probability of moving from x to y, where x is generated from pi, and the right hand is the unconditional probability of moving from y to x, where y is also generated from pi. The reversibility condition says that the two sides are equal and that the above result shows that pi is the invariant distribution for P. This result gives us a sufficient condition of reversibility that must be satisfied for P. And then next we're going to show how the Metropolis-Hastings algorithm finds a P with this property. Okay, so the Metropolis-Hastings algorithm uses a candidate generating density Q, and so that's specified by the user. And so the integral of that candidate generating density is 1, it being a probability density. And so when the process is at point x, the density generates a value y from the distribution qxy. And then if qxy satisfies the reversibility condition, we are done, but most likely it doesn't. And so we may find that for some x and y, the probability of moving one direction is greater than the other. So we can reduce the number of moves from x to y by introducing a probability alpha, which is less than 1, that the move is made. And then if the move is not made, the process remains at x. All right, so in order for the process to be reversible, the transition probability is listed below. So alpha is the minimum of the ratio at the top or 1. So meaning that just the maximum value for alpha is 1. Otherwise, it's the value here. And so that's listed over here on the right, where the pi y over pi x is the ratio of the target density for the proposed and current values. And then this right term is ratio of the how likely the proposed value is given the current state, and how likely would the current value have been were we at the proposed value. And so this right-hand part is what was added by Hastings in 1970. And so if you have I think we'll cover this later, but if the proposal distribution is symmetric, then these are the same, and so it becomes 1 and goes away. And it becomes just a Metropolis algorithm using this ratio. But if we have a non-symmetric proposal distribution, then this term comes into play and becomes important. Okay, and so to complete the definition, we consider the probability of remaining at x, which we listed earlier as R of x. And then so added up, the kernel of the Metropolis-Hastings chains becomes this expression. And then as we've discussed, as n goes to infinity, the pi of x becomes the invariant density of this this kernel. All right, so notes here. So the Metropolis-Hastings algorithm is specified by its candidate generating density Q, Q of x and y. And so if a candidate value is rejected, then the current value is taken as the next item in the sequence, which differs from our acceptance rejection where it's simply discarded. The calculation of alpha does not require knowledge of the normalizing constant of pi, since it's in both the numerator and the denominator. So it saves us having to find that normalizing constant for that distribution. And again, as I mentioned earlier, if the candidate generating density is symmetric, then Qxy equals Qyx, and so the probability reduces to the ratio of their probabilities based on the target density, and that becomes simply a Metropolis algorithm rather than Metropolis-Hastings. And in sum, based on the way we calculate alpha, if the jump goes uphill on the target density, we'll always accept it with probability of 1. But if it goes downhill, it'll be accepted with a non-zero probability, meaning that sometimes, even if the jump is downhill, we'll still accept it based on with a probability of pi of y over pi of x, right? And so we're showing jumps from x to y1 or y2, and so we always accept uphill jumps, but still sometimes accept downhill jumps. Okay, so this is the formal Metropolis-Hastings algorithm written out. So the user starts by selecting an initial value of x, and then we iterate through the following steps. So for I equals 1 to m, we repeat the following. First, we'll draw a candidate y from our proposal distribution q, given our current value of x. Next, we'll compute our acceptance probability using our formula for alpha. And then finally, we will either accept or reject that candidate. So if alpha is greater than or equal to 1, then it becomes 1. If you remember, it's the minimum of 1 in this value. And so we accept y, and we set our next value of x equal to y. And then if not, if alpha is between 0 and 1, then we accept y with a probability of alpha and reject it with a probability 1 minus alpha. And so in practice, what we're going to do here is we're going to compare this alpha value to a random draw from a uniform distribution, and then you use that to either accept or reject it based on this probability. And then this I thought was a pretty good graphic over here on the right, showing a random walk MC, where we're accepting and rejecting our different draws, and then with a large enough n, this converges to our target distribution, our posterior distribution, if it's a Bayesian inference problem. Okay, so a couple considerations. One is how long should our burn-in length be? Here's described as n sub 0, and then how long should we run our sampling for? And so one method is to start multiple chains from different initial values, and then we compare the variation in the draws. And so we can use the different draws to determine how long our burn-in ought to be, and how many samples we need to run to get a stable distribution. Another way is to make our burn-in and number of iterations functions, increasing functions of the first order serial correlation in the output. So the greater the correlation between subsequent draws, the longer we make the burn-in and the total number of iterations. And then I thought this was a nice illustration of a burn-in and then the probability distribution on some kind of multivariate data. This shiny bit being the highest probability. All right, and so then one of our other important choices becomes, how do we choose a candidate generating density Q? All right, and so we have multiple options, but perhaps the most common is a random walk chain, which is essentially our current value plus some noise from a distribution. And so here our Q sub 1 is a multivariate distribution, could be normal T or whatever. And then if it's symmetric, alpha becomes pi of y over pi of x, which again is the quote Metropolis algorithm. Another option is an independent chain. And so with that, candidates are drawn independently of the current location x. Third option is the psi function. And so using this, we're going to exploit some known form of our target distribution to specify our candidate generating density Q. And so pi of t is proportional to psi of t h of t, where h of t is a density that can be sampled, and psi can be uniformly bounded. So we set Q of x and y equal to h of y, which yields the following for alpha. Fourth, we can use an acceptance rejection method with a pseudo-dominating density. So there we use an AR step to generate candidates for an MH algorithm, and then we're going to cover that in a couple slides. It's one of Chib and Greenberg's examples or applications. Finally, we can use autoregressive chains. So if y takes a form a plus b x minus a plus z, where a is a vector and b is a matrix, and z has a q density, then q takes on this form. Of note, if we set our matrix B equal to a negative identity matrix, it produces chains that are reflected about the point A, and so that creates negative correlation between each successive draw in our chain. All right, another important thing is to consider the spread and scale of our candidate generating density Q. So the spread and scale of this density affect both the acceptance rate as well as the region covered by the chain. So if the spread of the density is too large, each candidate that is generated will be far from the mean, and then we have a low likelihood of acceptance. If the spread is too small, then the chain will take longer to traverse the support. So we have a higher rate of acceptance, and then it takes longer to sample, and then our lower probability regions will be undersampled. So both of these lead to slow and inefficient chains, whether it's too large or too small. And so the rule of thumb is to tune our acceptance rate so that it falls between 0.45, which is appropriate for a single variable, and 0.23, which for infinite variables. But the value would be as low as 0.25 in as few as 6 variables. And so generally we want acceptance rates that are closer to 0.23 than they are to 0.45. And then importantly, this ensures that the tails of our proposal density, it's also important to ensure that the tails of the proposal density dominate the target distribution. So in this figure to the right, you can see that the tails of Q are greater than those on our target distribution. which ensures that we get samples out into the tails and those aren't neglected. Here I'm going to switch over briefly, and I'm going to borrow from Ben Lambert's YouTube video. So here Ben Lambert's run a simulation with this target distribution. So this is the contour plot, and we see the high probability region, and all this blue is low probability. And then he's running his MCMC simulation. Green being accepted values, and orange being values that are rejected. And so that first example was one where the step was too small, the spread was too small, and so it was taking a long time to find the high density region. In this example, the spread is too large, and so it quickly finds the high density region, but then it has a low acceptance rate as it tries to explore the high probability region. So it's not exploring effectively or completely. All right, so here's an example of an appropriately tuned acceptance rate, where it finds the high probability region reasonably quickly, and then does a good job of exploring the region completely. Okay, and then finally he does a comparison with the three, with the spread that's too small, just right, and too large, and shows it shows how those draws play out over time. And so the just right is the closest to the target distribution over time. With the too small step, it eventually comes pretty close, but takes a long time to converge. And then with too long, we get a lot of noise in the distribution as it makes its draws. And so I've linked this video. I've linked to that video from the references at the end of this presentation. So if you feel free to check that out. He explains it better than I do. So. All right, so Chib and Greenberg also give us some applications of the MH algorithm, as well as some examples. And so this first application that they give us is an acceptance rejection application. And so here's where what do we refer to it as earlier? As the AR method with a pseudo-dominating density. And so what we have here is we're going to use an AR set to generate candidates for an MH algorithm. And so we want to sample from our pi of x is our f of x divided by some normalizing constant k. And so we suppose that c is greater than 0. It's a known constant, says that c, but our issue is that ch of x doesn't necessarily dominate f of x. And so ch of x is listed here in this dotted line, right? And so it dominates in the tails, but not here in the center of the distribution. And so we can define the set C for which it dominates. And so that's the union of this tail and this tail, right? And so the complement of C is this center portion of the distribution where C of hx does not dominate f of x. Okay, and so we're going to obtain candidate Z is independent of the current value of x. And so our candidate generating density becomes Q of y is f of y over CD for y in C, and then h of y over d for y not in C over here in the complement. And then again, y is independent of x in this case. And so since ch of x doesn't dominate f of x, here in the C complement, we add in a Metropolis-Hastings step for those y values. Okay, and so we have several cases here. So both x and y can either be in C or its complement. And so depending on whether x being our initial value and y the proposed value, right? So depending on where those are in that space determines what our alpha values are, right? And so for x and y both in C, then alpha is 1. For x not in C, so both are 1, right? For x not in C, y in C, the alpha of xy is C of hx over f of x, and alpha of y of x is 1. For x in C, y not in C, then alpha of xy is 1, alpha of yx is C h of x f over y. And so you see these two are the inverse of each other. And then for neither x or y in C, then alpha becomes the minimum of this ratio or 1, and then alpha of y of x is 1. And then formally this is described here. All right, another application of Metropolis-Hastings algorithm is to block at a time scans. And so here, Chib and Greenberg discuss the Gibbs sampler as a special case of Metropolis-Hastings, as well as combinations of the two. Okay, so we can apply Metropolis-Hastings to subblocks of our vector x, and this simplifies our search for candidate generating density and offers several other algorithms. And so based on the product of kernels principle, this allows us to take draws in succession from each of the separate kernels. And this is easier, so it's easier to find several kernels that converge to their respective conditional densities than it is to find one kernel that converges to the joint density. And so this gives us several special cases. One's the Gibbs sampler itself. And so we can show that if the kernel P1 and P2 fit this form, and then the samples are generated from the full conditional distribution rather than from a proposal density, right? And so the proposal density is the full conditional distribution. So the Gibbs sampler is in that way a special case of MH. I know that another case is using the MH algorithm within a Gibbs sampler, which the authors point out that this is a misnomer since Gibbs is itself a special case of Metropolis-Hastings, and so they're encouraging the community to stop using this term, but maybe it's too late. And then you'll recognize this from the homework as well, which uses the MH quote MH within Gibbs, and so for intractable conditional densities, you'll sample those with the MH algorithm, but other blocks which have closed forms, you can sample directly from their full conditional distributions using the Gibbs sampler. And then for those of you who love math and proofs, there's an extensive discussion of all of this in the paper. So if that's your jam, I'd encourage you to read it in its entirety, and it's linked from the end of the presentation. All right, so Chib and Greenberg give us two examples, and so this first example is simulated bivariate normal distribution, right? And so the distribution is described here on the left. So it's a bivariate normal with the means of the two the mu values at 1 and 2, and then with this covariance matrix. And then so our alpha acceptance ratio becomes the following, was the ratio or exponential terms from the normal distribution. Then Chib and Greenberg used several candidate generating densities, so that's Q, if you recall, and they adjust their parameters so that they have an acceptance rate between 40 and 50%. So they use random walk, pseudo rejection, as well as the autoregressive, which they found to have the best results. And then on the right here, they compare their results on the bottom with using the Cholesky approach on the top, and show that they achieve a very similar distribution of draws using the Metropolis-Hastings algorithm compared to the Cholesky approach. So just supporting the validity of the MH algorithm. Okay, and then here in their second example, they simulate a Bayesian posterior, which will be familiar to you if you from the homework. And so this is a stationary second order autoregressive time series model, which is from their 1994 paper. And so they simulate 100 observations from this model, which shows our y of t as a function of yt minus 1 and yt minus 2. So it's got some serial correlation as well as this error term. And then so the true parameters that they plug into the model are phi 1 equals 1, phi 2 equals negative 1/2, and then the error term is normally distributed about 0 with a variance of 1. And then then phi is from the real plane with the following constraints. And so it has this is our likelihood for the data, and then this is our posterior distribution. And so after they run this simulation, they get the following results for their estimate. So you get phi 1 is a little bit over 1, phi 2 is a little bit under negative 1/2, and then sigma squared is about 1.16. And so that's consistent with the true values from the model. And then I got a little bit of a chuckle out of this. They said that it took just 2 minutes on a 50 megahertz PC. It's a little bit of a throwback. So computers now are maybe 60 times that fast. And then I include some photos of Edward Greenberg and Siddhartha Chib, so you could see who we're talking about here. Finally, here I've listed the references for their paper as well as linked citations that are related to it. So that the paper itself is this first one, Understanding the Metropolis-Hastings Algorithm. And then also, if you're interested in that Bed-Lambert video on YouTube, that's linked down here at the right. And so that's it for this presentation. Hopefully it makes sense. Feel free to contact me with any questions, and then have a great day.